Hello, everyone. Welcome back. Today, we're going to be talking about the instantaneous rate of change. So, last time we talked about the average rate of change, which is basically the average slope between 2 points of a curve or a line itself, right? Um, and we know that to find the slope of a line, we use the equation slope equals to rise or run, or delta y over delta x, or whichever way you'd like to phrase it. So how do we find the slope of the curve? Well, the problem with finding the slope of a curve is a slope of a curve isn't constant, right? When we have a slope of a line, if we find the slope for one part of the line, that proves that that's a slope for the entire line because a line has a constant slope. The trouble with curves is that a curve has lots of different slopes depending where on the curve we're looking, right? So the slope of the curve is constantly changing, and therefore the slope of a curve has an infinite amount of answers, right? So on this point of the curve right here, looks like our slope is 0. On this point of the curve, our slope is, about 1-ish, right? On this point of our curve, slope is around like that, right? So the slope is different depending on where we are in the curve. So there's not just one answer, there's an infinite many answers for slope of a curve in most cases. So the tangent line is the straight line that most resembles the graph at a particular point. So for example, the tangent at this point would just be this line here, right? Because at this point it's a turning point, so it's just kind of flat, right? What about this point? Well, a line kind of like this would somewhat represent it, right? What about down here? Well, something kind of like this might represent that point a little bit well, and so on. And so the tangent is the straight line that most resembles the graph at a particular point. And we're going to learn an instantaneous rate of change formula that is going to show us that as best as possible. So the slope of a tangent line is equal to f of x plus h minus f of x over x plus h minus x, which is equal to f of x plus h minus f of x over h. But as h approaches 0, we find the slope of the tangent line, right? Not the secant line. And so our instantaneous rate of change is equal to the limit as f of x plus h minus f of x over h as x approaches to, as h approaches to 0. So that's our official definition, right? That's our calculus-wise definition. Okay, so that's our exact definition. Now, in this course, we're not actually going to use our exact definition. What we're going to do instead is we're going to get an approximate definition. We're going to do the approximate answers the approximate way. So, for example, if we're asked about the instantaneous rate of change right here, then what are we going to do? We're going to find the answer for here and here, so slightly above and slightly below, and go for that. But I do want to express that this is the exact definition, and that the way we're doing it today is just going to be the approximate definition, because this limit, right, this is not something we've covered just yet. So I'm going to give some examples of what we'll do for our approximations. Okay, so here it says a pebble is dropped from a cliff 80 meters high. After t seconds, the height s in meters of the pebble is represented by this equation. Calculate the average velocity of the pebble between 1 second and 3 seconds. Okay, so this actually goes back to what we did last day. This has to do with the average rate of change, okay, or the average velocity. So to find the average velocity, that's going to be the slope of our secant line, and that is going to be s of 3 minus s of 1 over 3 minus 1. So what's s of 3? Well, s of 3 is 80 minus 5, 3 squared, which is 35. And then s of 1 is 80 minus 5 times 1 squared, which is 75. So that is going to be 35 minus 75 over 2, which is going to be negative 40 over 2, which is going to be negative 20 meters per second, or 20 meters per second down is going to be our answer. Now, what about the velocity of at exactly 1 second? Well, we could use our limit definition, and that would give us the exact answer. But I'm not looking for an exact answer today because we haven't learned limits. I'm looking for an approximate answer. So what I'm going to do is we're just going to do it to the nearest tenth. So what I'm going to do is I'm going to find the average rate of change from 1.1 to 0.9. Okay, this is going to be our approximate rate of change, instantaneous rate of change. So to do that, I need to find what is S 1.1. Well, that's going to be 80 minus 5 times 1.1 squared, which let's grab our calculators and find out what that is because I am not sure what that is. 1.1 squared times 5, then 80 minus that number gives us 73.95. And then what about S of 0.9? That is going to be 80 minus 5 times 0.9 squared times 5, times negative 5, and then 80 subtracted is going to be 75.95. Okay, so therefore we have 73.95 minus 75.95 over 0.2. So that's going to give us, let's see, 73.95 minus 75.95 gets us negative 2 over 0.2, which is negative 10. So therefore, to the, this is going to be our answer. It's going to be negative 10 meters per second, or 10 meters per second down, because in this context of the question, it says a pebble is dropped from a cliff, right? So this pebble is not going up, it's going down. So of course our rates of change are all going to be negative because it's going downward. So that tells us that it's not going as fast at the exact point of 1 as it is from the point of 1 second to 3 seconds, right? Because here it's 10 meters per second down, and then from 1 to 3 it's 20 meters per second down. So it's going faster as it falls further, according to this equation, which makes sense because this is a quadratic equation. And so as we know, quadratics go, steeper and steeper and steeper the further we go along. So that makes good sense. Okay. Let's do example 3 as well. It says a toy rocket is launched straight up into the air such that the height s in meters at time t in seconds is represented by s of t equals negative 5t squared plus 30t plus 2. What is the velocity of the rocket at 2 seconds? Well, to do that, we need to find the instantaneous velocity at 2 seconds. So the approx rate of change to the nearest tenth is going to be s of 2.1 minus s of 1.9 over 2.1 minus 1.9. And let's see, well, what's s of 2.1? That's negative 5 times 2.1 squared plus 30 times 2.1 plus 2. Okay. So that's going to be negative 22.05 plus 63 plus 2. That's going to give us 42.95. And what about s of 1.9? Well, that's going to be negative 5 times 1.9 squared plus 30 times 1.9 plus 2. So that's going to be negative 18.05 plus 57 plus 2 minus 18.05 equals 40.95. So therefore we have 42.95 minus 40.95 over 0.2. Okay, so that's going to be 2 over 0.2, which is going to be 10 meters per second. This time we're launching up, so it's positive 10 meters per second, but it's interesting. We actually got the same answer both times, even though these are entirely different equations. So that's interesting, but there we go. So therefore, the velocity of the toy rocket at 2 seconds is 10 meters per second. And there we go. All right, so I want to do one more example like this, which is example 3, and then we'll be good. So example 3 says, a medicine is administered to a patient. The amount M of the medicine in milligrams in 1 milliliter of the patient's blood T hours after the injection is given by this equation, which this looks like another quadratic equation here. A says to find the amount of medicine in a patient after 1 hour of injection. Okay, so to do that, this has nothing to do with rate of change. They just want to know how much medicine is in a patient. So what is M, the amount of medicine, after 1 hour has passed? So to do this, all we have to do is sub in the value of 1 into the equation, which is going to be 1 minus 0.33, which is 0.67. So therefore, the amount of medicine after 1 hour is 0.67. And what was the units? It was, medicine was in milligrams. Time is in hours. Okay, so milligrams. Milligrams for 1 milliliter per milliliters. Okay, so there's our unit there. Okay, awesome. All right, so the next part asks find the average rate of change of the amount 1 hour after injection. So now they want the rate of change. So not the amount of blood that the patient or the amount of milligrams of the medicine in the patient's blood per milliliter. They want at this point just the rate of change. So to do that, we're going to find the approximate rate of change, which is going to be m of 1.1 minus m of 0.9 over 1.1 minus 0.9. So to do that, we need to plug these values in. So what's m of 1.1? That's going to be equal to 1 minus 0.33, 1.1 squared. So what's 1.1 squared times 0.33? That's going to be 0.6007. And then what's m of 0.9? Well, that's going to be 1 minus 0.33, 0.9 squared. minus 1, 0.7327. Good. Okay, so now let's plug all of that in. So we have 0.6007 minus 0.7327 over 0.2. And what's that going to equal to? Let's figure that out. 0.6007 minus 0.7327 divided by 0.2 gives us negative 0.66. Okay. Milligrams per second. And there we have it. All right, well, that is everything for today. Good work today, everyone. And next day we will talk even more about rates. Good work, everyone, and bye for now.